In this posting, we're going to be looking more at the flat plate in parallel flow. We've already considered this configuration where we have a surface and we have flow that is directed along the surface. It's parallel to the surface. And we treated the case where this surface was maintained at a constant surface temperature, or the isothermal case. And now we're going to look at how we arrived at the expression that we used last time for the laminar flow case. So last time we applied this correlation to solve a problem to find out what the heat transfer coefficient was for a specific case and what the resulting heat flux would be. So now we're going to look at where this expression comes from. So the first place we can get an expression like this, a correlation, is from experiments. And actually this is really probably the most useful and the most common, but it requires a lot of work. And so we can also consider the direct solution of the boundary layer equations. Now many times this isn't practical, but it is for the case of the flat plate in parallel flow for the laminar regime. In the laminar regime, we've already discussed the three boundary layer equations that we can apply. We've got a conservation of volume, or what's oftentimes termed a continuity equation. We've got the conservation of momentum. Now in this, I've written it in this form where we're saying that the change in pressure with respect to x is zero. So in other words, we're saying that the pressure gradient along the surface is negligibly small. And then finally, a conservation of thermal energy in the boundary layer. And again, I've removed one term that we had before, and that referred to viscous heating. And we said before that usually viscous heating is not a major concern. So with those slight simplifications to the boundary layer equation, then we can start looking at a velocity solution. So basically we're going to solve the momentum equation first. And your book details, gives some detail of one solution to this, one approach to solving this, obtaining the solution. And that's what's termed a similarity solution. And in order to approach this, we start by defining a new function that we're going to call psi. And that function, by definition, satisfies these relations. In other words, the partial derivative of that function with respect to y is equal to the velocity in the x direction, or u. And the partial derivative with respect to x times -1 is equal to the velocity in the y direction, or v. And this function psi, maybe you've seen it in your fluid mechanics course, is what's termed a stream function. And it's aptly named because it's constant along a streamline. And we remind ourselves what's meant by a streamline. A streamline is tangent to the velocity at all points. So if I am a particle and I follow the velocity at all points, I have to be a really light particle so that I don't have inertia of my own, but if I follow a fluid element, then I trace out a line that would describe a streamline. And so the stream function is constant along a streamline. So it has a very physical, very important physical meaning along with its mathematical definition. Now one useful thing for this definition, and actually it's part of where the definition comes from, is that the conservation of volume is automatically satisfied if we choose this this form for psi. Basically, we're saying that psi is satisfies the volume conservation by this definition. So then to progress in solving the momentum equation, we need to define a couple other variables, or it becomes makes our job a lot easier if we define a couple other variables. The first is what we're going to term a similarity variable, which we'll designate as eta. And the unique thing about eta is that it tells us, or if I trace a line of constant eta, Just like if I traced a line of constant psi, I said that was along the streamline. Well, if I trace a line of constant eta in the boundary layer, I find that it will follow a path where the ratio of u, the x velocity along this path, divided by the x velocity in the free stream, u infinity, is equal to a constant. And so u over u infinity equals to some function of eta. So eta is a combination of both y and x, and the free stream velocity and the kinematic viscosity. But as long as I maintain this combination of variables to have the same value, then I would find that u over u infinity had the same value. So as long as I satisfy that this relation is equal to a constant, then I would find that the velocity, the ratio of the velocity with respect to the free stream velocity was the same. Now finally, I define a variable or a function f, a variable f, that I could express as a function of eta if I wanted to, that's equal to psi divided by the free stream velocity times the square root of viscosity times exposition divided by u infinity. And if I then take these variables and I plug them into the momentum equation, I can arrive at an expression like this. And if I take the boundary conditions that are relevant to this case, namely that there's a no-slip condition at the surface, the velocity goes to 0 in both the x and y directions at the surface, and the free stream velocity is along the x direction, and that's u infinity, then I can express those as boundary conditions in terms of f. And I'd like to point out, we won't go into more detail as to how we solve this, but it is very useful to keep in mind some of the physical implications of the definition of the stream function and the similarity variable. And the momentum equation can be solved exactly in terms of an infinite series solution, as we've stated before, or it could be numerically integrated. And we're not going to give a really detailed description of this solution, but we are going to point out some of the important consequences. And one of the important consequences is that the solution tells us something about the thickness of the boundary layer. And again, if I don't put a subscript here, I'm meaning the velocity boundary layer. So this is the height above the surface by definition at which u equals 99% of u infinity. So if we have a surface and it's experiencing flow right at the leading edge of the surface, the velocity infinitely close to the surface is equal to the free stream velocity, and as the surface robs the momentum of the flow, then the flow slows down deeper and deeper into, or farther and farther away from the surface. We know at the surface the velocity is equal to 0 because of the no-slip condition, and that drag that the surface imposes on the flow propagates deeper and deeper into the flow. And the height of this boundary layer, where u equals 99% of u infinity, we just arbitrarily define that as the region in which the surface is having an influence on the flow, then that is given from this series solution or numerical integration. We find that that's equal to 5 times the distance from the leading edge divided by the square root of the Reynolds number, or 5 divided by the square root of u infinity over nu times x. So from that we can quickly see some implications about the boundary layer. One is, as we move further along the plate, the boundary layer grows with x. This is what we expect. The momentum is being sucked out of the flow the surface is imposing drag on the flow, and that's going to slow the flow down in a layer that keeps propagating deeper and deeper into the flow as we go further along the plate. It also increases with nu. This makes sense. Nu is our momentum diffusivity. It's the rate at which momentum diffuses along a gradient, down a gradient, or likewise we can kind of think of it as a generalized friction coefficient. It's saying how much drag force the surface applies on a slice of fluid that's trying to move along the surface, or how much drag force two fluid packets apply to each other, or how much drag force a fluid packet applies to another fluid packet that's trying to slide by it. And so as nu increases, we would expect that the surface would be more effective at pulling momentum out of the flow, at slowing down the flow further and further away from that surface. So as nu increases, the boundary layer thickness increases, with all other things being constant. And the other thing this tells us is that as the free stream velocity increases, the boundary layer thickness decreases. The free stream is able to bring more momentum in at a faster rate, and so that's going to decrease the boundary layer thickness. Now, once we have this solution, if we go back to our momentum equation, we can also solve for the shear stress at the surface. And we remind ourselves from fluid mechanics, shear stress is given by the dynamic viscosity times the gradient in velocity with respect to y, and this solution, series solution and numerical integration tells us that the shear stress at the surface is 0.332 times the free stream velocity times the square root of density times dynamic viscosity times free stream velocity over x. Or if we define the drag coefficient as the shear stress at the surface divided by the kinetic energy density of the flow, rho times u squared over 2, then we get an expression of the drag coefficient is equal to 0.664 times the Reynolds number to the 1/2 power, or I'm sorry, to the negative 1/2 power. So 0.664 divided by the square root of the Reynolds number. We can also consider the solution of the energy equation in terms of the variables that we've defined. So if we take the non-dimensionalized form of the energy equation and apply appropriate boundary conditions, namely the non-dimensionalized temperature is 0 at the surface and 1 in the free stream, then we have to integrate this numerically, but if we do so, then we obtain the solution for the Nusselt number that we used before. And again, we remind ourselves the Nusselt number is the heat transfer coefficient times x over k, or more generally the heat transfer coefficient times the relevant length scale. In this case, our relevant length scale is how far we are from the leading edge divided by k, and that's 0.332 times the Reynolds number to the 1/2 power, square root of Reynolds number, times the Prandtl number to the 1/3 power, cube root of the Prandtl number. Now this solution is only valid for laminar, and these boundary layer equations that we've derived are assumed steady flow, or were valid for steady flow, and therefore exclude the possibility of turbulence. And also this is derived for an isothermal situation. In other words, the surface temperature is constant. And we also have to impose one more limitation on this solution. It's valid for Prandtl numbers that are larger than about 0.6. It's not valid for really small Prandtl numbers that are relevant for things like liquid metals. So this solution, this relation, this correlation allows us to treat most of the things that we think about every day, gases, which would have a Prandtl number around 1. Air has a Prandtl number of about 0.7, so it's toward the low end of this range, but it's still okay. And water or oil or fluids like that, but we have to exclude liquid metals from this solution. We'll talk about the solution for those later. One other thing we say in those cases, before we had mentioned that the Prandtl number describes the momentum diffusivity divided by the thermal diffusivity, and so we could use it to say something about the thickness of the velocity boundary layer to the thermal boundary layer. And for these, this solution, for this laminar case with reasonably high Prandtl number, we can say that the ratio of these two boundary layer thicknesses are proportional roughly to Prandtl number to the 1/3, the cube root of the Prandtl number. So this, again, intuitively tells us that if we have a fluid with a very high Prandtl number, let's say oil, well, the oil is very effective at removing velocity, removing momentum from the flow. So its velocity boundary layer is going to grow very quickly. It's going to suck momentum out of the flow very quickly and slow down the flow a greater and greater distance away from the surface as we go downstream. But for oil, the thermal conductivity is not so good, and the thermal diffusivity is not so high. So we would expect its thermal boundary layer to be much smaller than the velocity boundary layer. In the case of a gas, where we might have a Prandtl number closer to 1, or to a liquid that has low viscosity, and we might have a Prandtl number closer to 1, then we would expect these two boundary layers to be about the same thickness. Again, we can physically relate that to the rate at which momentum is diffusing, being sucked out of the flow, to the rate at which thermal energy is diffusing and being sucked out of the flow. And we can also consider the average Nusselt number, and we did this explicitly. We went ahead and did the integral last time, where we evaluated the local heat transfer coefficient and then integrated it over x to arrive at an average heat transfer coefficient and then express the average Nusselt number. And we found that it was just 2 times the local Nusselt number, again, for the laminar isothermal case, and with the limitation that the Prandtl number is bigger than at least 0.6. Now we can also do the same integration for the drag coefficient and come up with a value again for the average drag coefficient that is twice as large as the drag coefficient that we find locally. So as we said before, we can't use that previous solution for cases that have very small Prandtl numbers. And the primary case that we are interested that falls into that category is for liquid metals. Now, liquid metals are interesting because they have a very high thermal conductivity and a very high boiling point, and that makes them useful in a number of high temperature applications. And a primary one where you may see them discussed is in high temperature heat pipes. And we'll discuss heat pipes a little bit later on in the course, but they're useful for thermal management, particularly for high temperature applications. And they're unique because of this really high thermal conductivity. And so we remind ourselves what Prandtl number is. It's the ratio of momentum diffusivity to thermal diffusivity. Or if we expand the kinematic viscosity and the thermal diffusivity, we see it's dynamic viscosity times, or that the Prandtl number can be expressed as dynamic viscosity times specific heat divided by thermal conductivity. So the unique properties of liquid metals revolve around this very high thermal conductivity. They tend to have a relatively low specific heat. I'm taking it as an example gallium here. Gallium is a metal that melts at about 30 degrees C, so in a little above 85 degrees Fahrenheit. So for applications above that, it makes a very interesting heat transfer fluid. Now, in the old days, we might have used mercury in a case where we might otherwise apply gallium, but mercury is highly toxic, and so we try to move away from the use of mercury in any application that we can. Gallium has comparatively much lower toxicity, and so it's more appealing for those sorts of applications now. And it has a thermal conductivity of about 30 watts per meter Kelvin, more similar to solid metals. And it has a specific heat of about 0.4 and a viscosity of about 1.4 millipascal seconds. So that gives us a Prandtl number of about 0.2. Sorry, I'm going to just redraw a line here, kind of excluded that text, which doesn't really make sense. These are useful for high temperature heat transfer applications. And so the Prandtl number for gallium around its melting point might be 0.02. Now, if we compare this to something like water, this is very small. Water at 20 degrees C might have a thermal conductivity of about 0.6. So what that's 50 times smaller than the thermal conductivity of gallium. And it has a much higher specific heat, about 4.2, and the viscosity is not very different. It's about 1. And so if we calculate the Prandtl number for water at room temperature, 20 degrees C, we get a Prandtl number of about 6 or 7. So we see here that we're over 2 orders of magnitude, over 100 times smaller Prandtl number. And so that condition now puts the Prandtl number much lower than the validity range for what we had considered previously for our laminar solution. So for liquid metals and other really low Prandtl number applications, we have a different solution. And this is expressed again for, specifically this is for laminar flow, as the Nusselt number, local Nusselt number at X. And again, this is for a flat plate. The local Nusselt number at X is 0.56 times a new dimensionless number we're going to introduce called the Peckley number. And that it's 0.56 times that Peckley number raised to the 1/2 power. And this is valid for low Prandtl numbers below about 5e to the -2. So gallium again would satisfy that, and Peckley numbers larger than about 100. And the Peckley number is defined as the Reynolds number times the Prandtl number, or if we expand these out, we can see that this is the velocity, free stream velocity times the length scale divided by the thermal diffusivity. Again, the kinematic viscosities cancel from these two terms, and so we're left with this ratio. And like all the dimensionless numbers, this has some physical meaning of the ratio of two quantities. In this case, the top is really saying it's about how fast things are advecting. In this case, specifically, we're interested in thermal energy, how fast thermal energy is carried with the velocity of the flow compared to how fast thermal energy is diffusing in the flow. So for Peckley numbers over 100 and low Prandtl numbers, this solution is valid for the local Nusselt number of a flat plate in laminar flow.